So today we will continue with chapter 5, which is the register transfer level design. And in this chapter we will look at introduction to the RTL design. So the register transfer design, or in short, normally we call it RTL, RTL design. We will look at how we design the complete digital system using RTL design method, right? Where it is comprises of controller and data path. And we will look at the RTL operations, and lastly we will look at the RTL design methodology. So this chapter is actually the introduction to what we call the RTL design. Yeah, so why RTL and what is RTL? This is uh, the question that we should ask when we look at RTL. So in the RTL design, or in designing a complete digital system, the most popular method is to use the RTL design methodology. So in the previous chapter before this, we have learned how to design the digital circuit. And the first one is the combinational circuit. In chapter 3. And we also in last chapter have learned the sequential circuit, right? How to design the sequential circuit. And now we will design a complete digital system where the circuit or the system comprises of both two type of circuit that we have learned before. So in RTL design, we will look at how the data is transferred, or if so in RTL design, we will learn how the data is transferred from one register into or to another register, right? So we will have the register, and we have another register. So our data will be in the register, so maybe come from the input device. So we have the data, for example, our data is 8-bit and our register is 8-bit. Right? So the data is in here in our register, and we will send this data to the combinational circuit, which can be a processing circuit. For example, the adder, the multiplier, the shifter, the subtractor, and so on, or any logic circuit, right, which are the combinational circuit. And from that, it will be transferred to, or it will be stored to a register. All right, and we can read the output from the register here. Right, so this is a typical digital system that we have the input and the data will be stored in the register, and from the register we the data is will go to the combinational circuit or the processing part here, and the output from this combinational circuit will be stored back to the register, and we can read the output from the register. So this is typical RTL, or what we call it register transfer level. Means that the data is moving from one register to another, to a register. All right, so we will look at uh, now we will look at a bigger picture or a complete design where we will have both combinational circuit and sequential circuit together in a complete system. Now back to this question, right? Back to this question. Why RTL? So the reason is that to build a complex digital system at logic level is hard. It's difficult. Yeah, to build a complex uh, digital system at logic level. What is at logic level? At logic level is that at uh, the equation level, yeah, the gate level, the gate logic level is hard. So we will look at more uh, higher abstraction, all right, which is the RTL level. So if we look at or where is the RTL in the in the design domain, right? So uh, in the digital design, at the lowest level of the design is of course the physical uh, the physical structure of the circuit, yeah, which is the layout of the circuit. So the layout of the circuit is actually just like when you have a schematic and you want to implement that schematic in the actual circuit, so you need to prepare the mask, right, to be printed on the printed circuit board. Okay, so what is on the PCB printed circuit board is actually the actual structure of your circuit. So that is also the same at the IC level, yeah, at the chip level, where we have the actual how the circuit is uh, connected to each other. All right, so that one is at the layout level, where we will not look at this layout level in our course, but we will look at the higher level because we want to design a complex circuit. So to design the complex circuit at the layout circuit is very complicated. So normally we will use the software to create the layout for us. And the next level, next higher level will be the schematic level, or in our case we call it transistor level. right? So this is the schematic level where it will show how the transistor is connected to each other to create a logic circuit. All right. So remember, in our case, we are in digital domain. So to implement digital number in hardware, so we need to use transistor, right? So the state of the transistor, whether it is off, it is on, will represent whether the logic is high or low. So the transistor on means that the logic is high, the transistor off is logic is low. So the schematic of the transistor will be the next level uh, of the design. And we also will not looking at this level in our course. Yeah, this will be covered in other course, which is called VLSI course. Yeah, very large scale integrated circuit. And the next level will be the gate level. Right, where it's comprised of the gate logic, right? This gate, for example, AND gate is connected to this gate and connected to this gate, and we have input and we have the output that is called the gate level, right? So this one we cover, yeah, it's covered in this course. Yeah, we have learned this already in previous chapter, how to design at gate level, right? And go up next level is the module level, yeah, where we group all the gate level to be a module. For example, a full adder module is connected to another full adder, for example, and the output maybe is connected to the multiplexer. All right, so this is module. This multiplexer also the module of the multiplexer. So that is the module level where we have also covered in this course. And go up next is the RTL level, where it will be covered in this chapter. And what is RTL level? And this is RTL level. Yeah. So inside here can be many module, connected to each other. All right. And we will look at the data that is transferred to this register, go to this processing circuit, which comprises to many modules, and the output is going to another register, right? So that will be uh, or what we will do in this chapter. And later in chapter 6, we will go to even higher level, which is we call it higher level design, which is at the algorithm level, right? But will be in the next chapter, which is chapter 6. So here we are in chapter 5, RTL. So again, why we learn RTL? Because to design a complex system at the layout level is extremely difficult. And when you go up next at the transistor level, also very difficult. At the gate level, we have learned already, right? To design a complete complex system at gate level is not that easy. Right? At the logic level, for example, yeah, we have learned already when we design the circuit uh, from the equation, for example, or when we want to derive the logic equation. So if the input is small, then we should be able to derive the equation and derive the gate schematic, right? Gate circuit. But if we have the input that is big, For example, we have 10 input. So to uh, derive the equation for that problem is almost impossible. Okay, so now we need to go up higher level, which is the module level, where the design of complicated circuit is more easily because we can use this module and try to connect to each other like this. For example, we have FA module where we have designed previously at the gate level, and we connect to the another gate module, FA module, for example, and we have also the module of multiplexer, and we can connect to each other like this. And this will be a lot more easier, yeah, because when we want to try to design a circuit, for example, the whole circuit like this at the gate level is actually very difficult, right? So the module level uh, is more easier as compared to the level below, right? But later on, when we move to RTL design, we can even, yeah, create a more complicated circuit or a complete system for our application, right? So for example, we want to design a digital system based on a certain specification. So the best way is to design at the RTL level, right? So that is why we have this RTL design uh, methodology. So RTL design is when we view the system in terms of how the data is transferred and processed at higher level than logic. So this is exactly uh, explained by this, yeah. And now, what is RTL? Actually, I have explained to you already. So this is uh, what is RTL, larger design are built by interconnecting the smaller module component at the level of register, multiplexer, decoder, adder, etc. Right? So register, multiplexer is the uh, the one inside here. Yeah, multiplexer, adder, decoder will be in here, and we have the register. Okay, so to design a digital system, a complete digital system, normally we will have two components. Yeah, two components that is very important. First is what we call the data path. Yeah, we look at data path first. So the data path is the our circuit. For example, our circuit to process some data, right, where the data is coming in here and go to this register, and we have the processing unit here, and we have another register here, and the output here may be feedback to this processing unit here and go back to the register and so on, right? So this is called a data path, yeah, data path unit or data path circuit, right? And actually before this we have designed this uh, kind of data paths already in chapter 4. For example, we learned how to design the register, and in the previous chapter, in the chapter before, chapter 3, we have learned how to design this. This is the processing unit, maybe with maybe an adder, maybe a combination of adder and a subtractor, or maybe a combination of adder, subtractor, multiplier, and other logic circuit, right? So depend on the specification. But in order to uh, to make this work, all right, because we need to sequence the operation of the of the data here in order to get the output. Yeah, so the data must come to this register at the right time and must be, yeah, must go to this processing unit at the right time, and also at what time we want to load the data into this register, and at what time we want to send the data to the output, right? So that is the sequence of the operation for this. Yeah, because without the sequence, so this data is meaningless. This circuit is actually meaningless, right? So we need the sequence of the operation of this circuit. So to do the sequencing, all right, or to control the sequence of the operation in this circuit, we need another circuit called the control circuit or control unit, or sometimes we call the controller. All right, so we will need another circuit that is called the control unit, and this control unit is actually a finite state machine, or FSM, where we also have learned in chapter 4. All right, and this together will form the complete digital system. And in this chapter, we will learn how to design this, yeah, the complete digital system. All right, now we will look at the RTL operations, which is the which will define the operation of the data pass component. Right? And it actually comprises of three main elements. The first one is the register set. Yes, we need to have the register. Yeah, the operation that are performed on data in the register. So the operation that will be performed, whether we want to load the data into the register, or we read the data into the register, or we want to shift the data in the register. All right, and we want to send the data into the processing unit, process, and we get the data back here. All right, that is the operation that perform on the data. And the last one is the very important one also, which is the sequence of the operation. Yeah, just like I said before. So we need to sequence the operation of this circuit, all right, in order to get the output that we want, right? So now come to the RTL operation, and the operation is represented by what we call the RTL notations. Okay, so this is the notation that we will use in order to represent the operation in our design. All right. So for example, if we have two registers, X and Y, okay, let's say we have two registers, and this is register X, this is register Y. When we want to transfer the data from, in this case, is from Y to X. So let's, for example, we want to transfer the data from register Y to register X. And let's, for example, the size of the register is 8-bit. And if I write the data, yeah, I have the data inside, and I represent my data in hexadecimal number. For example, the number is 1A, right? So this 1A is 8-bit data, yeah, because 1 in binary is 0001, A is 1010. All right. So when I want to transfer the data from Y to X, such that I will have 1A in X. So the operation is called data transfer, and the notation is like this. Here, where we use the arrow representing the data that is transferred from Y to X. All right, and remember, in digital circuit, when we said we transfer the data, it is actually copy. Is actually copy, yeah, because when we transfer the data from Y to X, in Y, after we transfer, we will not have 0 in Y, but we still have the previous data. Yeah, we still have the data in Y, but we just have the data in X. The reason is that when we learn to design the register, a register in the previous chapter, so when you have a register, right, this is a D flip-flops, right? So when you have the data in, for example, A, so the output here will be A, right? Depending on the clocks. So when you get the data from here, for example, you send to another register. So A here will remain A unless you reset this register, all right? Or you put another data into the register. You change the data to B, then you will have another data. But if you only read, yeah, or send to another register like this, A here will remain A unless you change the input or load another data into this, right? So that is the meaning of that. So remember, in computer or in digital circuit, when we say transfer, it is actually a copy. Now, next is this. Let's, for example, we want to connect wire, and we have many wires, and many wires is actually a bus in a digital system, right? So, for example, we want to do something like this, where we have many wires. Four wires, right? And this is called M bus. Yeah, and M bus is 4-bit, and we can have M bus 0, M bus 1, M bus 2, M bus 3, right? And if we want to connect to another bus or another wire, and this one is called, for example, B bus, M bus, or art bus. Yeah, it's called art bus. So the notation that we use is art bus equal to M bus, right? It's easy. So this means that we connect the bus, this bus, into with this bus. Now the next notation is to clear the content of a register, and for example, our register is X. So this is the notation that we use. Yeah, means that we move 0 or transfer 0 into X. And then I forgot to tell that in RTL notation, so this is called operand, yeah, operand, the right hand side, and this is called the destination. So the data will move from the source operand to the destination from the right to the left, yeah, this. So we will have that's why we have something like this, yeah. So we will not write like this, yeah. This is universal, where when we want to set the data is moved from y to x, so y will be at the source operand and it will be at the right hand side, and it will be moved to the left here using the arrow like this. Okay, now the next operand is to um, move the result of this operation where the content of x plus with y, and then we save x, right? The content of the x register plus y, the content of y register, we add to register the result of this operation, add x plus y, is saved or transferred to x. So if we look at the circuit will be it looks like this, yeah, to represent that operation. So we can have two register where the first register is register x and the second register is register y, and we have an adder here. So we add the output of x with the output of y, and the result is go back to register x. So that is the meaning of that notation, and the circuit will be will looks like this. And the next notation is to read the content of the memory into register X. So in chapter 4, we have learned already how to create the memory in memory circuit, yeah, in Verilog. So this is the notation to read the content of the memory location or memory address 100F into the content of register X. All right. So remember in chapter 4, we have learned how to design a memory where the memory is or looks something like this, where we have many location, and each location can store 1 byte data, for example, for 8-bit, and each location has a unique address. So for example, this is address 0, this is address 1, address 2, 3, 4, until depend on the size of your memory. So for example, if your memory is 1K in size, so the last location will be 1023, yeah, in decimal. In hexadecimal will be FFFF, right? If you look at the So if you want to get the data from, for example, this memory name is MEM, location number 5, for example, right? And this is our register. The name of our register is register X. So if we want to get the data from memory location number 5 or address number 5 into this register X, so the notation is this X, the name, and the location, which is 5H in hexadecimal, or you can just write 5. This is correct also. If you want to get the data from location number 4, so the notation is 4. If you want to get the data from location number 1023, so you can use decimal number, which is 1203, or you can write in hexadecimal, which is 3F, right? Or you can use the calculator, 1203, which is 3FF, yeah. So 3FFH in hexadecimal, right? So that is how the complete circuit to do this. We will learn in later, right? Where of course you need to have the data bus that is connected to here, to the memory, and also you need to have the address decoder, right? That will decode the address and activate the one that we are accessing. Okay? So if in our case, if we want to access number 5, for example, so X, so the value in the address line will be number 5, right? So that it will, this address decoder will decode, or if the value here is 5, it will activate this location number 5, so that you can get the data from here and put in X. If you want to get from 1203, so the value in the address line will be 1203. Get, and this go to the decoder, and it will decode, or it will activate this location, and the data will go to the to the register X, right? But we will look in the detail when we start design and start designing our circuit in this chapter. Okay, so that is how we do. And the next notation is also to get the data from the memory, but now instead of we have the location, the memory address in here in the square bracket, but we have another register, the content of another register. So what is this mean? This is means by this. This is also called an indirect addressing, right? So in this case, for example, we have two register. One is X, another one is Y, and inside Y we have 5. Okay, so if we write X and we want to transfer the data from memory and then in the bracket is y, means that in here is actually number 5. Yeah, number 5. So we actually get the data from location number 5 and put in x, right? And if in our register y we have 1 0 0 0, so means that here is 1 0 0 0, or y is 1 0 0 0, means that we get the data from location 1 0 0 0 and put in x. That is the meaning of this. Okay, so straightforward. Next is the shift operation, where we want to shift the content of register X. So we can use either one. So this one also correct, this one also correct. So this is shift right, shift to the right. So look at this symbol, means that to the right, from the left to the right, the content of register X to the right, and 1 here means that we shift 1 bit. Yeah, we shift 1 bit. So what is mean by that? Means that we have a register X, and let's say this register is 4 bit. Yeah, make it simple so that we have only 4 bit. This is bit number 0, 1 2 3. So when we say we shift right, for example, the data in here, initially we have 1 0 1 0. So when we do this, means that we shift 1 time to the right, and the result will be here we shift out, so, and here we shift to here, so we will have 1 here, and 0 will shift to here, so we have 0, and 1 here will shift to here, so that we have 1. And from the outside, it depends on our design whether we want to have arithmetic shift, where uh, we maintain or preserve the sign. This is called the sign bit, or MSB, or we want to have 0, that we call the logical shift. So this is a shift 1 time, but if you shift 2 times, for example, you have something like this. This means that you shift 2 times, or 2 bit to the right. So what happens is that this one, of course, go out. This one shift 1 time will go to this, but you need to shift 2 times. So 1 also go out. So this one will go to here 1 time, go to here 2 times. So this 0 will go to here, yeah, and this will go to here. So now you only have this, and the this one we have 0, because it's a shift from the outside here, right? That is shift 2 times. When you want to shift 3 times, means that you shift 3 times. For example, this 0 will go here, here, and go out. Here will go here, here, and here. That is shift 3 times. Okay. This is shift right. What if we want to shift left? So shift left is this. So if we want to shift left, so we can use this. This is shift left one time. If you want to shift 2 times, you can have this, right? So that is shift right or left. So the next one is to transfer the data also. Yeah, this is transfer the data from Y to X, but this is with condition. This is condition. Okay, so this is very useful where when you want to, for example, yeah, if A equal to 1, then you want to transfer the data from X to Y. So this is called condition. Yeah, this is condition, meaning that you will do this operation only if this condition is true. If A equal to 1, so you do this operation. But if A equal to 0, you will not do this. That is the meaning of this. Yeah. The next one is also the transfer. So this condition, before we go to this, this condition you can have made any operation. Yeah, this is only example. Yeah, RTL notation with condition. Next one is the transfer also, or any other notation, but this one happen in this. This is state. Yeah? So the state can be any state. All right, can be any name. So this is only example as 0. You can have S1, you can have state A or any name that you want. All right, and also any operation. But this is example of, for example, in state S0, you want to transfer the content of Y into the content of X. So this is how you write, right? And the last one is also any operation here, but in this example is the transfer from Y to X. So here also the same. We have this operation in S0, and this is happen only if only the condition is true. So this is condition A and B. So this means that if A and B is true, or we can write A, B, yeah, A and B is true. So we transfer X to Y, and this one is happen in S0, in state S0. We do this, and we learned already what is state S0. State S0 is the state in the finite state machine, FSM. Okay, that is the RTL notation. Now we will look at the example, but before we will go to the example, let's have a short break, 5 minutes, right? Then we come back and look at this example.